One of the important application of the motion under a constant acceleration is the problem of freely falling objects. The freely falling object is the problem of the motion of the object near the Earth's surface. This problem can date back to the time of a great scientist, Galileo Galilei. This guy. By dropping two objects with the same shape but different weights from the top of Leaning Tower of Pisa, he showed that those objects hit the ground at the same time. So this is a picture of the Leaning Tower of Pisa. So it means that if you drop, or Galileo dropped, two objects, this one and this one, down to the ground, it will hit the ground at the same time. It's not depend on the weight of the object, but the object should have the same shape, and the weight of both objects have to be it means that it have to heavy enough to overcome what we know now that it have to overcome the effect of the air resistance. Okay. Using our modern language of physics, this result implies that every object near the Earth's surface moves under the same acceleration, and we call that acceleration g. This means that every object moves near the Earth's surface. We have a constant acceleration, which we call g. Its full name is gravitational acceleration g. Okay. And near the Earth's surface, we have that g is approximately constant. We use the word approximately because we will see later that actually g depends on the height from the ground. But if you are close to the Earth's surface, the value of g is not change much. This is because the Earth is very large, and the Earth's radius is very large compared to the height. If the Earth's radius is very large compared to the height of the object, g is approximately constant. We will see this in more detail later. As an acceleration, the gravitational acceleration is a vector. The gravitational acceleration is a vector. So you need to specify the direction of a vector. However, when we talk about g, the value of g, when we talk about the value of g, the value of g is always positive, okay, and is approximately equal to the 9.8 something, okay. So when we talk about the value of g, we will have that g is equal to the 9.8 or maybe 9.81 meter per second square. But if we talk about the g as the vector, we will specify the sign. So if we talk about the vector g, this is a minus of 9.80. Okay, so if you want to write it as a vector, you have to explicitly show the sign, the negative sign. Okay, you have to explicitly show the negative sign here. But if you talk about the value of g, it is the positive number 9.8. Okay. There is a point about the motion near the Earth's surface that many people always misunderstand. That is about the acceleration and the velocity of the motion. For example, if you throw an object upward like this, if you have an object and you throw it upward, you know that from your experience, everybody knows this, that the object will move up to the maximum point and then move down. So you can see that the velocity changes all the time. First it's decreasing and then it is increasing. So the velocity change. And at the top of the motion, the velocity here is equal to 0 at the maximum height. But if you look at the acceleration y is always equal to the minus g, and this is a constant. It's not changed. The acceleration y, ay point down, and the magnitude of the ay is equal to g. Okay, so the acceleration not change, is not changed, but the velocity change. Some people think that at the top of the motion the acceleration is also 0, but it's not correct. It is the velocity that is 0, but the acceleration is a constant throughout the motion. Okay, we now reach the final section of this chapter. So far, we have derived the kinematic equations using geometry and some simple algebra. In this section, we will re-derive those equations using more powerful methods that we will use throughout our study. It is a method of the calculus. Let's start with looking at this VT diagram. Okay, this VT diagram. This represents the motion of an object from the initial time ti here to the final time tf here. Now, let us divide the time from ti to tf into n interval. Please note that all these intervals are not necessarily equal. Even in this picture, it seems that they have the same, they are equal. I mean, the time interval are equal in this picture, but in general, it's not necessary. So, from this figure, we have this relation. We can write down the delta x, which is equal to the xf minus xi is equal to the summation of Vxn average time delta Tn. Okay, this value Vxn average time delta Tn is the displacement of the object during the time delta Tn, right? It's the displacement of the object during the time delta Tn. And when we sum up the displacement for all time interval, we sum up this displacement for all, we sum up this displacement for all time interval. It must equal to the total displacement, that is the xf minus xi. Okay, this Vxn average is the average. It is the average velocity over the time delta Tn. Okay, so from this equation we will use the concept of the calculus to derive some relation. I mean, to derive the previous relation that we have discussed before. You can see that if we take the limit delta Tn, mean all delta Tn approach 0, we will get that delta x is equal to the limit of all delta Tn approaching 0 of the summation of the Vxn average of delta Tn. Okay, note that we will have the same result for the displacement. I mean, for the total displacement. It's not depend on the size of the delta Tn as we discussed before. So when we do the limit process, we also have the same value of delta x.